If our common practices are problematic, what's the better way? A good sample size plan has at least three parts: an estimation of a sample size that is adequate for the research question, a stopping rule, and a priori guidance on what will be considered valid data. Sounds easy, right? But what exactly does it mean to have an adequate sample? Surprisingly, statisticians have developed more than one way of answering this question. There are several prominent approaches, and this is an area of active development in inferential statistics. The most well-known approach is based on statistical power, but there's also planning for precision, planning for evidence, and other approaches that we won't have time to cover in this workshop. Each of these requires some explanation, but note that all are based on consideration of effect sizes. So let's take a moment to talk about this foundational issue. An effect size is a quantitative answer to your research question. For example, suppose you wanted to know if nucleus accumbens volume relates to drug abuse behavior. Typically, we frame and answer this in qualitative terms. Is there a relationship? We then report a p-value and use it to make a qualitative yes or no decision. In addition to this qualitative approach, though, we can take a quantitative approach. We can ask, to what extent or degree are these measures related? The effect size for this type of question is Pearson's R and its confidence interval. No matter what your research design, there's always a corresponding quantitative question and effect size answer. Here's an example from the Journal of Neuroscience. The research question is if knocking out the PRP gene reduces seizures in a mouse model of Creutzfeldt-Jakob disease. We can answer the qualitative question with a p-value, which is statistically significant, so we say yes, there is an effect. The quantitative question is how much of an effect. To find out, we have to look at the descriptive statistics. The disease model had 10.9 induced seizures. Those with the gene knockout had only 3.9. That's a decrease of 7 seizures with a margin of error of 3. That decrease of 7 seizures is the effect size that indicates the degree to which the knockout gene protected against seizures. Effect sizes apply to complex designs as well. Here's an example from a factorial analysis examining brain by sex interactions. Researchers wanted to know if long-term potentiation is moderated by sex. They induced long-term potentiation in the hippocampi of male and female rats. Again, this would normally be reported with a p-value, which did show a statistically significant interaction. But we can also express this quantitatively, asking how much does sex moderate plasticity? In males, the LTP protocol increased the field EPSB slope by 225%. That's a massive increase. In females, LTP was also induced, but the change was only 160%. So the interaction is the difference in these effects. Gender rate moderates plasticity, changing the degree of potentiation by 65% with a confidence interval from 47 to 83, meaning that we can be pretty confident that there's a fairly dramatic gender difference in the expression of LTP with this protocol. So, effect sizes are pretty simple. They're just a quantitative answer to your research question. Any p-value you obtain actually has a partner effect size and confidence interval. It can sometimes be helpful to communicate and compare effect sizes in standardized terms. As an example, consider the math portion of the ACT, a standardized test of college readiness that's popular in some parts of the United States. In 2018, as usual, the average for males taking the ACT math portion was higher than for females, a statistically significant difference. That's the qualitative conclusion, one that almost always makes the news. But let's look at the effect size. How big was this difference? Well, the average math score for males was around 21.5. How did the women score? Around a 20.5. That's a 1-point difference. Is that a big deal? Well, that would take some knowledge about the ACT and how it's scored. It's measured on a 1 to 36 scale with a standard deviation of about 5. Experts do their best interpreting effect sizes like this, in raw scores, because they know their scale of measurement. But to compare effect sizes and to communicate across assays and fields, it can sometimes help to standardize the effect. One popular metric is Cohen's d. This simply divides the effect size by the standard deviation, expressing the effect in standard deviation units. So with a difference of 1 point and a standard deviation of 5, the effect size here is just 2/10 of a standard deviation. We could also calculate r squared, the coefficient of determination. In this case, it's 0.01, meaning that 1% of the variation in math scores could be attributed to sex. Another useful metric is overlap, looking at how much the distributions of the two groups overlap. In this case, it's 92%. One really nice way to think about effect sizes that I like is in terms of the sample sizes needed to study. If you wanted to have an 80% chance of detecting the difference in math ACT scores between men and women, you'd need about 400 participants of each gender. So that puts effect sizes in a kind of resource allocation framework. I've dwelt on this topic because it's not possible to thoughtfully plan sample sizes without a strong sense of effect sizes, both in general and especially within your own research field. So let's go down the road of building your effect size intuitions. Here I've aligned some of the different ways that we can standardize effect sizes. Now let's talk about how we can interpret them. Cohen famously formulated labels for small, medium, and large effects at 0.2, 0.5, and 0.8 of a standard deviation. He cautioned, though, not to dogmatically apply these labels. What's really essential is to build a sense of effect sizes in your own field for the assays that you regularly use. Here, for example, are some effect sizes related to sex and gender. As we just mentioned, differences in math performance have a Cohen's d of about 0.2. In published animal studies, sex differences on cognitive tasks like the water maze, they tend to be a bit larger. But not all sex differences are subtle. Total brain volume in humans differs by sex by an entire standard deviation. And height is really dramatic, more than 2 standard deviations. But of course, there are also null differences as well. For example, once we adjust for body mass, the difference in hippocampal volume between men and women seems to be almost exactly 0. Now, this is just an example. What I urge you to do is to complete this exercise in your own field of study. For example, here are some more effect sizes from my home field of neuroscience. A meta-analysis reporting the wide range of effect sizes that are typical in cognitive neuroscience and comparing them to those reported in the medical field. Fear conditioning, which is a very popular assay in neuroscience, has a very large effect size, but that's nothing compared to long-term potentiation, which has an effect size so enormous and so clear that we really don't need much statistical analysis to consider it. Effect sizes turn out to be really important, not just for sample size planning, but for evaluating research results and for formulating clear and quantitative theories. Recognizing this, there is an increasing consensus that we should always be reporting effect sizes and uncertainty, either with or possibly even in place of those pesky p-values.